So let's talk about the technique that allows you to study membrane potential and actually specifically what's happening in the different channels. So the technique is called patch clamp, and there are 3 variations we're going to talk about. What I want you to see on this slide is how it's set up. So you have this pipette tip, and I'll be drawing it like this. So it's a little pipette tip. There's liquid here, it's attached to an electrode, and it can measure, the membrane potential. Okay, so the difference in the charges. And this is just showing you you're really patching or clamping onto a very small part of the membrane. And then you can perhaps add things to the cytosol or add things to the extracellular solution based on the variant you're using, and test what happens when you change the environment. Maybe you add a drug, maybe you add a some kind of solute concentration. So the first variant we're going to talk about is the whole cell recording. Okay. What I want you to understand is this is not specific to any certain channels. So all this is going to tell you is what happens to the membrane potential of the entire cell when you put the cell in different environments. So what's happening here is you see that you attach the patch clamp, you get a little suction, and you actually break the membrane so that now you can measure what's happening across the membrane. And so what this is happening is you've got your cell, my cell, and I have my little clamp attached to it, and I could put different things into this media and determine what's happening to the cell membrane. So is it letting ions in or ions going out? Is it blocking channels? But again, it's nothing specific. It's the whole cell recording, whole cell response. If you want to look at specific channels, there's 2 different techniques. The inside-out recording allows you to manipulate or add your drug or your solution, the cytoplasm or the cytoplasmic side of the channel. So now we're going to look at very specific channels. And how we do that is we apply the patch clamp and then we pull it away. Okay? So we're removing this little channel and part of its membrane from the rest of the cell. And so what this would look like in a dish is that, you have your piece of membrane here with your channel, and then you can dip it into different solutions, and you're exposing the cytoplasmic side to whatever you're studying. So inside out. The third variation, again, looking at specific channels, because again you're clamping the membrane and you're removing a piece, and in this case the way you remove it is you get some of the membrane, you get your channel, and then this reseals, right? And so now the outside is exposed. So when you take your little dish with whatever you're studying and you dunk your membrane piece right here with the channel, you're seeing what is happening to the outside or the extracellular part of the channel, and does it cause a change in ion flow, things like that. So you can measure change in charge. Okay, so this is the outside out. So the outside of the membrane is out versus this one where the inside of the membrane was exposed. Okay, so that's the technique that's important for this chapter and for being able to study some of these channels and what's happening and if drugs affect specific channels. So let's go back to talking about the action potential. We've talked about resting potential. We've talked about this yellow graph that shows an action potential where the membrane goes from negative to positive back to negative. We've talked about hyperpolarization, which is an overshoot, so it gets a little too negative and then comes back to resting. There's a couple other potentials I want to talk about. The first one is the threshold potential. The threshold potential is a value that the membrane potential has to change greater than in order for an action potential to happen. So remember, as you're thinking about these are all based, this action potential is going to be based on the opening and closing of voltage-gated ion channels. So if you only have a little bit of change in the voltage on the membrane, it's not enough to get enough ion channels open to make an action potential. Okay. So the threshold potential is the value that has to be passed in order to initiate an action potential. So if the signal is not strong enough, you just go back to resting. A couple other potentials that are talked about in the book, and I just added it to this graph, something called the sodium equilibrium potential. And the first thing I want you to notice is that this line is above, greater than the peak action potential. Depending on your source, it's a positive 55 to 60 millivolts. And at this membrane potential, sodium would be in equilibrium, right? No net movement, moving back and forth equally. Membranes never reach this level because other ions are moving. So other ions are making this value go back and forth and back and forth. Likewise, down here somewhere is the potassium equilibrium potential. Depending on the source, it's somewhere between minus 75 to minus 90 millivolts. Key is it's below hyperpolarization. Okay, so this is where if the membrane reached that, potassium would be at equilibrium. Just like the sodium equilibrium potential, it's never reached because there are other ions moving that affect this value. So most important is threshold, but I want you to understand what these equilibrium potentials are as well. All right, so let's look at how this is all happening. Okay, so super busy image. We're going to walk through it. We're going to start down here at number 1. Okay, this is your resting state, and we talked about resting state is produced by the potassium leak channels primarily, and then also the sodium-potassium pump and the sodium leak channels to give us that negative 60-ish membrane potential value. So what we're adding to this picture now are our voltage gated, sorry, didn't want it to go that long, voltage, yep, it's not going to go, ion channels. Okay, so these voltage gated ion channels, we have both sodium and potassium. And what it's showing you is that there are more sodium than there are potassium. And we'll talk about this a little bit more. All right, at resting state, both types are closed. Since they're voltage gated, you have to have a change in the voltage across the membrane in order for these things to open. So as the cell is getting signals and passes threshold, you start to open these sodium gated channels. Okay, So you can open a few, but if you don't get past threshold, you don't move on. So this is depolarization. Okay. Sodium is coming into the cell, making it more positive inside. As soon as we hit that threshold potential, you get rapid opening of sodium channels, of the sodium ion voltage gated ion channels. I'm just going to write sodium channels for short. Okay. And as you get more positive in, then more sodium channels open. And this is called the Hodgkin cycle. Okay. So it's kind of this feedback loop. We open more, we get more positive, we open more, we get more positive, we open more, we get more positive. So the Hodgkin cycle is happening right here. Notice that the potassium channels are still closed. At a certain point, the sodium channels become inactivated. So remember, inactivated is beyond closed. So now they've got this little plug here. And now we can't get any more sodium coming in, and the K+ channels open. So the potassium voltage gated channels open, and now we've got potassium moving out, and we get repolarization. Right? So now we're going back to negative because the plus charges are leaving. Okay. So as the potassium's moving out, our membrane potential is becoming more negative. The undershoot is right here, hyperpolarization. Okay. And we just keep getting a little too much potassium out. Eventually, the potassium channels get closed, actually inactivated and closed, and everything goes back to the resting state. Okay. Now, the sodium channels also become just closed, not inactivated, right? So everything here is just now closed. So you have this opening of the sodium channels, and then opening of the potassium channels and inactivation of the sodium channels, closing of everything, returning back to normal, and this is called an action potential. When you look at action potential graphs, you may notice something called a refractory period. There's an absolute and there's a relative. And what's happening in the refractory period is it's a time that you cannot start another action potential. Okay, so even if the cell got a signal right there on the membrane, right here, especially right here, the sodium channels are inactivated. So you absolutely cannot start another action potential. The relative refractory period, here is where the sodium channels are becoming just closed, so they're no longer inactivated. But because of this hyperpolarization, you have to get a much greater signal than when the membrane's at resting potential in order to stimulate another action potential. So relative means it's possible but unlikely. The absolute refractory period, nope, cannot get another action potential started. Okay. I provide you this image. It's way too busy for me. I have a hard time kind of following it, but I think some people like visuals. You can click on the link at the bottom here, and it talks more about action potential propagation, but some people like to see this visual of the ions moving in and out across the membrane. Okay, we're going to stop there. We're going to come back to propagation of action potentials, and then we'll finish off with synapses and neurotransmitters.